A little fun here today. Today our story is going to be about two very intimately related processes that have major influence on the surface of Earth. The rock cycle and plate tectonics. These two processes work together, they drive each other, and they are responsible for making Earth the most geologically diverse of all the planets, the most beautiful of the planets, and perhaps most diverse anywhere, actually. They are responsible for some beautiful, beautiful places. Now, if it weren't for the rock cycle and plate tectonics, our planet would be a very different place than it is today. Instead of looking like this, it actually would look more like this. Well, let's do a little refresher right here just to make sure we're all the same place here. Show you a cutaway of Earth's interior. And as our refresher there, the way down at the bottom, you can see down here, you can see the radius of Earth is 6,378 kilometers. And there we have, at that location, an inner core which is solid, iron and nickel. It provides a tremendous amount of mass for the planet, makes the planet fairly dense. Above it, though, is a liquid core, again of the metal, and the inner core actually is rotating at a slightly faster speed than the rest of the planet. That produces all kinds of eddy currents, and it produces electric fields that eventually shoot out as big magnetic fields going way out into space. Above that, we end up with a mantle, and it's multi-layered, but the top layer of the mantle is more plastic, and it moves very, very slowly, but it can move. Things can move through it. Then we have the asthenosphere, and right above that is actually it's the crust that kind of blended together there. The crust is solid. It is thicker over the continents and thinner under the oceans. That's basically what Earth is all about. Now, if we didn't have the rock cycle and plate tectonics, well, we would not have this kind of stuff right here sticking up. We would not have the land masses. Okay, here's the eternal question. Which came first? Rock cycle or plate tectonics? And actually, there is an answer to this question. It's the rock cycle. In order to have plate tectonics, you have to have a solid surface. So where do you get the solid surface? From the formation of the initial rocks, which would be igneous rocks, fire-formed rocks, rocks that have formed from the cooling of the magma. Earth at one time, in its earliest history, was just simply a molten ball of material. And when it began to cool, the crust formed first, and that's eventually becoming broken and starting to move around. Well, let's take a look at the rock cycle right now, and then we're going to relate that directly to plate tectonics. So here's a cutaway diagram of the Earth, and we'll start with a circle there. And we're going to begin with magma, which is molten material deep down under. And when the magma cools, it may rise up and so forth, but when eventually it cools, it forms two kinds of igneous rock. Intrusive rock, which is rock that is still below the surface, like granites and things of that sort. And extrusive would be like lava that pours out of volcanoes and vents and various sorts. Eventually, we have weather, and weather can break down the rocks, weathering rather I should say, can break down the rocks, and there are many forms of weathering, which we'll get into in the presentation. And then we have erosion, which is, once you break it down, you move it somewhere else, so those two work together, and it deposits it. Sedimentation, that's the term there. You get sedimentation, and that pile of stuff that's laying in the ocean basin right there is called sediment. Then we have a term called lithification, which you may not be familiar with, but basically it means eventually you pile up so much stuff there and there's cement and all that, it forms rocks. It solidifies into rock. So we have the term sedimentary rock. Now, because things are moving around, because we have plate tectonics, sometimes that rock gets thrust back down under Earth, and we'll get into the process of that a little bit later. And it begins to heat up, and it begins to be experiencing pressure. And when that happens, we reconvert the rock into something else called metamorphic rock. So now it's very different than it was a few moments ago, or some time ago. And if you push it down far enough into the Earth, eventually it may, oh, by the way, that thing called subduction, I'll forget that term right now. But when we push it down far enough into the Earth, we have melting, and the melting returns it back into magma, And when it cools, it becomes igneous rock again. So we basically have a cycle. But the cycle is not really neat and clean like this. There are shortcuts. For example, that arrow right there, igneous rock can be remelted and become magma and then go back to being igneous rock again later. Sedimentary rock can be weathered and eroded and so forth and become sediment again. Metamorphic rock can be weathered and eroded and become sediment also. Sedimentary rock can be heat melted to the point where it becomes magma. And igneous rock can be changed into metamorphic rock. So there's lots of different shortcuts here. Now, as you look at that, boy, that's really confusing. So many arrows and things going every which way, and there'll be a test on this later. Now, we'll simplify it a bit, and that's really what it looks like. So you got the igneous rock, it cools, you got igneous rock and the weathering, erosion, sediment, lithification, all that, and all the shortcut arrows. It's a cycle that goes on constantly. It's extremely slow, except when you have volcanic eruptions. The whole thing is extremely slow, but over time, we got billions of years, over time, lots of major things happen as a result of it. Now, where do we fit in plate tectonics here? Well, here again, back to the inner Earth again. And the inner core and the outer core are extremely hot. The outer core in particular is molten rock. Heat works its way up through convection currents, one of the ways of heat transfer. You know, you have things like radiation, convection, conduction. Well, convection is when the hot material begins to physically move upward, and because this mantle area is plastic, the heat goes with this moving material, and it comes up here. So near the top, we have magma upwelling, and let's say that this is the mid-Atlantic ridge, that ridge that runs right down the Atlantic Ocean to the North and South Atlantic. So we got North America over here, we got Europe, Asia, and Africa over here. And when that material comes up, it pushes, and it actually builds that ridge in the middle there, builds a mountain ridge under the water, but it pushes the rock this way, it pushes the rock that way, and starts making large plates begin to move there. They move very slowly, about the rate at which your fingernail grows, but they move. Over on the side, in fact, by the way, that's called ridge push, is the geological term for that. But over on the side, we have subduction right over here. And what happens is that the thicker continental plates begin to push into the thinner ocean plates, and it kind of pushes them down. And that's called subduction. So this plate's going down, and that one's kind of going over this way here, and you get this crumple zone right there. And furthermore, there's one more thing can happen, and that is the slab itself by its own weight can kind of pull the rest of it down. So let's say you put a tablecloth on a table and you don't have it quite balanced and you let it go and the whole tablecloth kind of pulls itself off. That's what slab pull is about there. It can pull large rock masses down. Well, here's a map showing approximately the tectonic plates of Earth, and there are about 14 big and small ones out there. But let's take a look at some of the locations. Like the Mid-Atlantic Ridge runs right along here. And it basically parallels the outline of the continents. Well, they kind of push apart right there, and they go that way on each side. That's that ridge push thing that we saw before. Then on the other side here, like this part of the plate is pushing into the Pacific plate. So they're pushing together, and one's going under the other. And then there are other kinds of plates where they run side by side. So here we got the convergent boundary where the plates come together, and one goes under the other. We have the divergent boundary. Here's one down there. You can see these arrows all through here. Now they're pushing apart, so there's material coming up from below pushing them apart. And then we have a transform, which means it one goes this way, one goes that way. The three types of movements of the tectonic plate. Now let's take a little closer look at this. Remember we said about how things slid under there, so this stuff is sliding down, and this part is going up over the top. And think of this as a really major traffic accident. You got a big vehicle, small vehicle, and the small one is pushed underneath, kind of pushed down, and the big one there kind of crumples. Those are the mountains. But also, because you have things being pushed down, you got a lot of heating taking place, molten material working its way back up, and you got the volcanoes. So this is one of the major ways in which the land is built up. One of the ways. The other way is, of course, sedimentation, eventually building big piles of sediment that become rock, like what's going on in the Gulf of Mexico. That's a big thing called a geosyncline, but what it is basically is just a big basin full of sediment that's building up. And eventually that will become a mountain range a long time from now. So, don't worry about having a mountain view cabin over by the lake. But anyways, okay. Now, as a result of this, we get a bunch of stuff happening like faults and folds, which are part of the process of shaping the rock on Earth. And I have a few models right here, and I'm afraid the lights are, I hope you can see these. Wanted to show you how this stuff works here. First off, let's just talk about sediment. Let me move my stuff around here. There we go. Can you see that well, I hope? Okay, good. All right, so I've got a box right here. It's plastic on both sides. And I've got my sediment, which happens to be black beans. But you can use almost anything to show the idea here. So I'm going to just kind of, we have weathering, erosion taking place. Material is being collected and moved and transported and eventually dumped into different locations. So we have a nice layer built up there of one particular color right there. We'll take another color. So there's been some change, or rivers have moved and new material comes through. And meanwhile, there's also, say, in ocean environments, like living things and eventually get washed in. Here's an elephant that died. Oh, poor thing, it died. There it is right there. And this water buffalo died, and here's a giraffe. And these eventually get buried, you know, and they become fossils. They turn to stone. Now, much later, you know, there, so you can see a couple of them sticking out there. Then there's another change right here to continue our layering. And now we're getting to more modern times, so we have other kinds of fossils that occur, like, for example, here's a Dodge Dart. We'll put that right there. Okay, and that gets there. Eventually, that will be nothing more than a car-shaped rust spot. So we end up with something that looks like this. And we get this layering. But basically, it's one layer after another. And now one of the principles of geology is that the layer on the bottom is the oldest layer, and the layer on the top is the youngest layer. Real simple thing. Okay, fine. Along comes more weathering and erosion, and it kind of goes in here and carries material off. And what happens is that sometimes, well, I'm making a mess there, but you get layers that will begin to be exposed. So when you go out west in particular, you'll see layer after layer after layer. It's because of weathering and erosion. Takes away part of it to show you the walls. The Grand Canyon is a great example of that, where you get one layer after another that's exposed by the running water. So that's our layering right there. Let's put that off to the side here. In time, the layers get changed because something happens to things with plate tectonics. I'm going to set my microphone down for just a moment here, and I've got some bath towels here. These are at Anna's, like $5 a bath towel. Cut them all up and put a couple of threads in there to make sure they don't fall apart. And I'm going to show you what happens if you provide pressure to this, which is like the continents are pushing against each other, and it can distort the rocks. Rocks can flow, and I'll show you what. This happens. Now you might think, rocks can flow? Well, yes, they can. Got a piece here of silly putty. And silly putty is kind of cool because it's a good material, kind of shows a little bit how rocks can flow and so forth. It's fairly solid. It bounces and all that. Fairly solid. And if I put some pressure on this thing, I'm going to stretch it in this case. Stretch it, and stretch it, and stretch it. Silly putty really does a nice job stretching. Okay, rocks can do that. If you produce enough pressure or pulling tension for a long enough period, very slowly adding that pull, you end up with that. It'll actually stretch. Now I'm going to make a little piece right here, and this time I'm going to show what happens when the forces are rapid. So it breaks. Silly putty is a lot of fun to work with. And just for the fun of it, I have some more silly putty. It's rolling across the room. I thought it was going to bounce higher than that. Oh well, thank you, Nancy. Well, this is silly putty, right? It bounces and so forth. And I'm just going to take this and place it on the table here. Just a moment, please. It's hanging over the edge. Occasionally take a look at that. Watch what happens. It's not going to happen. Well, it's actually starting to move now. Okay. Let me put this over here. One more model to show you. And that's this one right here, which is made of wood. It's a way of demonstrating what happens when the forces are too fast for the rocks to withstand. So this is my faulting model right here. And all I got to do is push on it like this, for example. And, well, and it breaks like that. Or if I pull on it like this and keep pulling, it goes down like that. This is very common, especially out in the West. You can go out there and see rocks, and you see this big slice, and then there are rocks that are kind of offset from each other. That's faulting, and we'll talk about that in a bit. So we can have the lights back off, please. I'd appreciate that. Okay, so let's look at now faults and folds. We'll start with faults right here. If you have compressional stress, you end up with something that looks like this over here. If you have tensional, you're pulling it apart, it can look like that. And if you have shear, which is side by side, it can look like this. And we'll look at more detail each one of these. There are terms in faulting that geologists like to use, and they call this a normal fault, which means you get a crack there. And it's a tensional thing. It's pulled apart. So one wall goes up, one wall goes down, in other words. Or, they both go together, or just one or the other happens. And usually what happens is miners will go out there and find these things, and they'll tunnel down along the fault plane itself, because quite often you'll find hot material coming up from below after the fault was made and depositing things like gold and silver and so forth in there. So they'll mine these things. And that gives us the names of the faults, partly. They have what is called a hanging wall, which is if the miners are walking down this thing, the wall over their head is called the hanging wall, and the wall they're walking on is called the footwall. So to remember what the fault is, which one it is, think of the word fun. Footwall up normal. Simple. Okay, now let's look at another one called here's actually one of these faults. And by the way, this picture I took more than 40 years ago. I found it recently. And it shows a normal fault here. So look over there. You got that big rock layer right there. And the look over here is where it continues. It's kind of covered up with sediment. But this whole mass just simply dropped down, or that one went up, or both at the same time. And there's a bit of a drag. Whoops, I went too fast. One back here again. There's a bit of a drag effect right here where part of this wall got pulled down as this one was dropping. That's called a drag fold. Then we have a thing called a reverse fault, which is, it goes like that, which means, and of course this memory device doesn't work as well anymore because people don't usually think about our four-time president, Franklin Delano Roosevelt, but if you go FDR, footwall down, reverse. Okay. It's also called a thrust fault. And the idea of a thrust fault is it's kind of thrust over, this side of the rock layers here are kind of thrust over those rock layers. And you can see the drag folds when they're doing that. And here's an example of that. Now this is kind of vertical, this is out in Europe, but it's kind of vertical and you've got those drag folds, but the fault line here runs right along through there. And quite often you find a lot of vegetation there because the rock gets ground when that happens, and then you get some soil in there. And here's one that I took just in Wisconsin a couple of weeks ago. This is called Van Heist Rock, and these two pieces have moved in relation to each other, but when they moved, they weren't standing up like this. In fact, they were more on their side, and then everything got bent and stood upright. And I'll show you how we know that. Well, first off, I'll get to that in a moment, excuse me. We'll do a strike-slip fault. This is like what happens in California. San Andreas Fault. Here's the fault line. And here's how they move. And I'll show you a river there. There's a river, you can barely see it there, a river running right through here. I'll show you what happens to the river. It moves like that. And that happens up there. You can see there, if you look at the picture very carefully, there are other rivers where you see where they go like this. Make that shape where this side is moved over so the river follows the fault line. And there you are. Now, when you have folds and so forth, sometimes they get confusing because of the way things weather in a road. An anticline is a dome, a syncline is a basin. That's what they mean. But let's say we have clouds coming over and it starts to rain and over millions of years, and the thing weathers and erodes, and you end up with what looks like a whole series of basins right there. But actually, this is still the anticline because you see the rock layers going up, they just are missing right there. And they're going down there and so forth. Here's what that looks like from space. And that's like in Wyoming. So you got these interesting curves right here. It's like looking at an anticline. You kind of go up and over the top, and then you down into a syncline, and then to another anticline there, and so forth. By the way, I got that slide out of order. I wanted to show you this one here before. This is in Wisconsin also, but notice that the wall has all these rippling shapes to that. That's an old beach. These are the ripple marks from an old beach preserved in sandstone that eventually became quartzite, and then the whole thing got stood right up on end. So that's near that other rock that I showed you from Wisconsin. Okay, part of the rock cycle, a big part of it is the weathering and erosion. So let's take a look at what weathering and erosion is. Weathering simply is a breakdown of material, sediments and soil, and if it's soil, it's got to have organic material in it to be called soil. Otherwise, like it's sand, like a beach is not soil. So it's got to have that organic material. And you got your physical weathering and you got your chemical. Physical, like heat and pressure, frost wedging and so forth. Chemical would be like acid rain. Here are a couple examples of that. That's frost wedging. You go outside and you walk around, see a big boulder and it's cracked in half, probably frost wedging. Water got in there, froze, cracked and pushed the rock apart. Here's a statue. I don't know what it's made out of exactly, but you can see how badly worn that statue is. That's a result of acid rain. And plants, like lichens, these are a symbiotic relationship between an algae, let's see, I think it's an algae and a, what? And a fungus. And a fungus, yeah, that's right. I have a metal block there. Anyways, what they do, one of them is, the algae will make food, but the fungus will actually make acids that actually eat into the rock and provide an anchoring point. And these break down rock over time. And here's, maybe a little hard to see, but again in Wisconsin, there's a nice tree right there. And you can see all the roots interlacing into the rock layers. They're all over the outside. And they're spreading apart the rock. So that's part of the weathering process, breaking things down. Now for the erosion process, all it is just, it moves everything to a new location. That's all it is. So you got rainfall, rivers, water waves, glaciers, and so forth. Here are a few examples. This is a bank that's just simply been washed away by rainfall. Here's wave-cut cliffs. So the ocean right there has actually produced that wide beach by washing into the cliffs. And a glacier moves extraordinary amounts of rock and debris as the ice moves down the valley very slowly. And here's wind erosion, rocks like this. These are called hoodoos. And then we have the most powerful superhero of erosion. Not me. We're talking about right there, you see, you know. This picture is of me in Taos, New Mexico, about 3 weeks ago. I'm actually riding a hot air balloon at the moment, and we're over the Rio Grande. And we actually touched down in the water. Really kind of cool to do that. Anyway, a better view from the air. We rose up pretty high, but that's the Rio Grande going along through here. The Taos area is over there, and that's the Rio Hondo. But this water erosion is running water is a huge. Oh. Yeah. Thank you very much. Took me a moment to catch on to that one. Okay. All right. Let's see, what are we talking about? Okay. So you got erosion like Grand Canyon. Eventually you dump it. That's a satellite picture, color enhanced of the Mississippi Delta. And it gets dumped, and that becomes new rock. So it's a replacement part of the cycle all the time. Always replacing. Things get broken down, get replaced. There is one more kind, though, that occurs. It's kind of a rarer kind, impacts. And I just thought I'd show you. This is the Barringer crater out in Arizona. It's a very recent crater, so it's really sharply defined. Most craters on Earth are either wiped away completely by weathering and erosion. This one here is partway. It's called Manicouagan in Canada. And that's all that's left of this particular impact crater. Eventually it'll be wiped away completely. And impacts, you know, are very common actually, relatively geologically speaking in time. If we didn't have weathering and erosion, Earth would look more like this, or could look like this. Of course, forget about the water part, but we'd have all these kinds of craters forming like the moon has. So we'd have that many. But we've worn them away by weathering and erosion over the years. Now there is one big story though, and that's the dinosaurs, like what happened to them. And most scientists believe that an impact triggered the extinction of the dinosaurs 65 million years ago. That is the tip of the Yucatan Peninsula And the impact took place right there. About 10-mile wide asteroid maybe, or a big comet hitting there. And it just completely devastated planet Earth. I mean, a wave of water would have washed maybe 100 feet high over this part right here. It would have just gone right across the Gulf of Mexico, a tsunami like you wouldn't believe. And everything was washed away. You can go way north of here and find debris left over from that. All around the world are trace elements of iridium, which is a very uncommon rock on, or element on Earth, but they are common in meteors and so forth, and it's spread out over Earth in a very thin layer. The closer you are to this, the thicker that layer is. The farther away, the thinner it is, but it's all over the Earth. Well, that is, well, they think was the destruction of the dinosaurs. Most scientists think that. All right, we're going to change gears a little bit here. Hey, teacher, I found this rock. Oh, I forgot. May I stop one moment, please? I got to show you one more thing. I forgot it here. It's hiding behind some other stuff. I have a large iron ball which is covered with aluminum foil. This has to do with impacts. And I have another iron ball which is rolling around here. Oh, there it is. It's just rusty. These are actually railroad ball bearings. So I got a rusty ball and a ball bearing with aluminum foil. I'm going to smack them together to show you about impacts, why they can cause so much damage. It's not just that you hit it and knock things around. It's also the heat that is generated by the impact. It's really amazing. I'm going to smack the two balls together and I want you to see what happens. Now it takes a couple of times for me to get it right sometimes, so be patient with me. Missed it. Well, it's done. Anybody here watch Breaking Bad? A few of you do. If you heard that, remember the early season about thermite? That's thermite. The rusty ball and the aluminum, when you mix them together and you provide heat, actually ignites that. That's thermite happening right there, a thermite reaction. But it took heat to generate that, and I had to hit it just right to get enough heat, enough friction to do so. Well, impacts do that. Okay, let's go on here. I found this rock. What is it, teacher? Is it valuable? What's it made of? Is it a meteorite? Are those crystals diamonds? What's it good for? Where did it come from? Well, you found it, but you tell me, you know. Related questions: why does the earth shake? What caused a volcano? Or how are mountains made? What's a big wave, tsunami, and so forth? And this goes on and on and on, the questions that kids have. But kids like rocks. And that's why we have a little drawing here for rocks over there. Rocks are fun, and if you have big samples, you can really teach a lot from them by just looking these things over. So I thought what we'd do is we'd have a little kind of mini quiz show here. Name that rock. And your answers are igneous, sedimentary, or metamorphic. I'm going to show you some rocks and let you think about it for a moment, and then I'll tell you what it is. And kind of help you understand a little bit about how you identify rocks. So when they come in there, if you can give them those three right there, one of those three names, that's pretty good. And that's a good thing. That'll stop them. If you can add stuff to it if you want to, but those are the three main things they need to know. So let's start with this one right here. What is that? Igneous, metamorphic, or sedimentary? And I can understand that a bit. But okay, you came up with an answer. That happens to be an igneous rock. It's extrusive. It's vesicular basalt. And vesicular means these little bubble holes all through here. Those are called vesicles. And basalt, it's a very dark rock. It is basically a lava. But it's full of gas when it's formed, and the gas gets frozen inside the rock when the rock cools off. So that's vesicular basalt, lava. Let's try this one. Yeah, it is sedimentary. I heard somebody say that. So sedimentary, it's called a conglomerate. And it's made up of pebbles that were washed down from some rock deposit, but they never got ground down enough to sand or to finer particles than that. And they piled up. Smaller particles kind of got mixed in with them and cement, and it formed this conglomerate. Now this rock has been sawed, so you can see that nice smooth surface. And those pieces of rock that make it up are called clasts. C-L-A-S-T. That's not something you need to know, but that's what they're called. Okay, what's this? Now you might be fooled a little bit, but you'll still get the right answer. It is sedimentary. Those lines right there are not sedimentary layers. Those are lines of black minerals, dark ferromagnesium minerals that have migrated through the rock. Sometimes you get a stain in the wall of your house, let's say. It's moisture moving along and leaving little lines and so forth. Well, that's the same thing right here. In the rock itself, the iron and magnesium minerals have moved a little bit over time and formed what is called picture rock. So it's kind of neat. It's a sedimentary rock, picture rock sandstone, and gives that banded pattern to it. That's a real rock. It's an igneous rock, it's extrusive, and that is Pohoihoi lava. This lava flowed out like very thick pancake batter, and it rolled over on itself and cooled, and those are the folds that are in like the pancake batter. And again, look at all the vesicles in there. That would be a sign this is an igneous rock. So Pohoihoi lava. Pohoihoi is a Hawaiian term for lava. It's a slow-moving lava. Like in the movies when people are, like the fiction movies and the lava is slowing down, you want to be in front of the lava flow that's made of Pohoihoi. It moves very slowly. The lava moves a lot faster, and you don't want to be in front of that. And that is the name of it. It's called Okay, this is igneous. It's granite. Now, geologists will say to you, be careful, don't take everything for granted. I'm sorry, but we got geologist jokes. We got to have those. Okay. This one actually is metamorphic. It's banded quartzite. At one time it was sandstone, and there's migration of minerals like we saw in that one before. But you look at the bands, they're alternating colors. That's your key. If you see a bunch of horizontal lines, it's probably sedimentary, but when they keep changing colors like this, that's metamorphic, because when you're heating up a rock and pressing it, minerals tend to move inside the rock and kind of get together. Like minerals kind of get together with each other and make the banded effect. And by the way, this line right here is a straight line. I had it sawed off so I could stand it upright on a desk. But that's quartzite. Now this quartzite, old sandstone that became quartzite through metamorphism, and in the metamorphic process it also got bent, which is another clue that it's metamorphic. If you look at these things right here, those are snails actually, which would indicate sedimentary. Turritella is the name of the snails, fossil snails, sedimentary rock. This is a little tougher one here. We actually have a couple of different things. It's called quartzite breccia, and it's both igneous and metamorphic. The metamorphic part is this stuff right here, which is quartzite, sandstone that eventually got converted to quartzite. And this is quartz that the rock got broke, and then hot solutions came up from below, igneous solutions, and deposited quartz in veins, and became this. This one will get you, probably. It is, in fact, sedimentary. But what are all those scratches right there? I didn't put those scratches on there. That was done on the bottom of a glacier. The rock was dragged along, and other rocks kind of scraped together, and the lines tend to be all in the same general direction. That is a glacially weathered limestone. Glacial striations. Okay, we're back to igneous again, volcanic glass. If you have the material coming out, not full of bubbles, but really cools really fast, it makes a glassy material. No crystals have a chance to form, so it's glass. Volcanic glass or obsidian. Sometimes you go to rock shops, they'll call this Apache tears. They polish it. Get ready for another geologist joke, I'm going to warn you. This is metamorphic. It's called GNEISS. That's a nice rock. It's pronounced nice. Yes, it is. Again, look at the bands. Black band, white band, black band. That's your key that this is actually what was once granite. And the minerals migrated as it became a metamorphic rock. Now this one really is kind of bent, so a little bit of folding went on here, but it turns out it hasn't converted yet to a metamorphic rock. It's basically limestone, And these bands and so forth got pushed around a bit, but those kind of are soft, and it shows the bedding. But notice all the colors are the same, so that would be indicating sedimentary rock rather than metamorphic. Oh, this is tough. Okay, I'm going to admit this one. This is an igneous rock. It's native copper from Wisconsin. Actually, it came down from Michigan, landed in Wisconsin, and it's quartz and feldspar surrounding it. It's a big nugget of copper. A couple more here. Now that one looks kind of odd. I'll show you another direction. And if you look at there, it's a beautiful grain pattern here, and I heard somebody say it. It says petrified wood. So it's sedimentary rock. And, oh, I pushed the button too fast, so I guess I've given this one away. But again, look at the banding, metamorphic banding taking place. Now here's really big crystals. That's mica there, and that's feldspar right there, and some more mica there. This is another igneous rock. It's called a pegmatite because it has really big crystals, but you got quartz, feldspar, muscovite, mica in it. And this is the vein, like in one of those fault veins, filled in with this kind of stuff, made these really big crystals. If you look at the texture, it looks kind of sandy, and we have ripple marked sandstone. This is an old beach, and it got preserved, fossilized beach. Now, one thing I mentioned to you, that this, I'm not going to ask you to tell me what this is sand, obviously, but the good thing about sand is it's a collection of little rocks and minerals. And if you have magnifiers, you can see all kinds of amazing things of sand. If you collect sand from different locations, you'll find sand with shell fragments, you'll find sand with quartz, feldspar, minerals that may be magnetic, all kinds of cool things that you can do with sand. And it's a great way of looking at rocks and minerals, but looking at small pieces of it and not having your whole house filled up with rocks. Just a little bottle would be good enough for this case. One more thing to show you, and that's this right here. If the kids bring this in, try to be gentle. Not rocks. These are building materials made from sand, clay, gravel, tar, crushed stone, and so forth. But, you know, they are actually, were one-time rocks. So that's how you can make it sound better. But those are, if you find, like, for example, those little thick patterns on the back of a thin sheet, that's manufactured rock for flooring, you know. And this is concrete from a road, and it's a brick, and that's an asphalt mixture, and that's a brick right there. So kids can find this stuff and sometimes get confused about that. Well, we've taken a rather rapid journey through the topic of plate tectonics and rocks and minerals. In a moment, we're going to be giving away the rocks that we have on the table.